Hello, Hello, Lana. Welcome once again to Manifested e-learning platform. My name is James Kenyani. We are going to continue with our lesson on reflection and congruence. And today we are going to look at symmetry lines of a rhombus. So the objective of the lesson is to enable the learner to identify and even construct the lines of symmetry of a rhombus. So the lesson will help the learner to identify the lines of symmetry of a rhombus. So they say seeing is believing. That's why I have the rhombus here cut out from a piece of paper. We know a rhombus is a quadrilateral whose sides are equal. A quadrilateral, because the angles at the vertices are not 90 degrees. But a quadrilateral with angles, right angles at the four corners will either be a square or a rectangle. So in this case, we have that quadrilateral. We call it a rhombus because all the sides are equal and the opposite sides are parallel. So we want to go step by step and look how many lines of symmetry can we get. So I'll fold it along the longest diagonal. I've folded it along the longest diagonal. And yes, is that a line of symmetry? Yes, because those two halves have similar proportionate similarities are seen in them. I'll fold it along the shortest diagonal. Shortest diagonal. Yes, I get two halves which are equal. So what is your conclusion? A rhombus will have two lines of symmetry, one along the shorter diagonal and the other along the longer diagonal. Now, I'm going to compare it to another sister quadrilateral. It is called a parallelogram. If you compare the two, you can see a clear difference. For the rhombus, the sides are equal, but for the parallelogram, this one, the sides are not equal. Let's try to find lines of symmetry of a parallelogram. So when you fold, either the left part should map exactly on the other ones. Let's try and fold along the one of the diagonals. Let's fold along one of the diagonals of a parallelogram. Does it map exactly? Yes or no? A big no, isn't it? Let's try to fold along the longest diagonal. And the case for the other longest diagonal is no. So what do we discover? We discover that a rhombus will have two lines of symmetry, but a parallelogram does not have any lines of symmetry. That's one of the most important things we notice. A rhombus has two lines of symmetry, one along the shorter diagonal, and another along the longer diagonal. as demonstrated. One along the shorter diagonal and another one along the longer diagonal. In comparison, we found that a parallelogram, a parallelogram does not have any line of symmetry. That's what you should discover, the utmost discovery you make. A parallelogram does not have any line of symmetry. So we shall just show them here. It is a mark on the rhombus to show that all the sides are equal. So you've seen one of the lines of symmetry is along the shorter diagonal. Along the shorter diagonal. Another one is along the longer diagonal. What do you discover? The lines of symmetry or the diagonals always meet for a rhombus at 90 degrees. So we say a rhombus can just say two lines of symmetry. You can also draw the parallelogram, its sister quadrilateral. Those two lines just shows this one is only equal to that and this one is equal to that one. But that one we had just one mark to show that all the sides are equal. So from there we just write for a parallelogram, no line of symmetry, as I demonstrated using that piece of paper. So notice that. What do we notice? We go to objective. We've discovered that a rhombus has two lines of symmetry, one along the shorter diagonal and one along the longer diagonal. The diagonals meet at 90 degrees. We've just discovered a parallelogram will have no line of symmetry. So for the assignment, so we'll construct that rhombus of side 6 centimeters and angle ABC 60 degrees and show the lines of symmetry. So as I end the lesson, notice that a rhombus will have two lines of symmetry. A parallelogram, none, does not have any lines of symmetry. So at that juncture, I end the lesson, but don't forget what you've learned. So go work on the construction and let's meet in the next lesson. Thank you for the audience and bye-bye.
How are you, learner? My name is Dickens, and we are looking at effect of heat on salts in today's lesson. We want to start by looking at, first of all, the effect of heat on nitrates. So effect of heat on nitrates. Effect of heat on nitrates. So the products of heating nitrates generally depends on the position of the nitrate in the reactivity series. In that, those nitrates of the more reactive elements like sodium and potassium will produce different products. Those nitrates of those elements which are in the middle of the reactivity series will also give you different elements. And then lastly, those nitrates of those metals which are least reactive. So we are going to look at those three categories. Remember, we have said the products depends on the position of the element in the reactivity series. So we start with the sodium and potassium. So Lana, we need to know this, that the nitrates of sodium, and potassium, these two decompose on heating to give you two products. The products are the corresponding metal nitrite and oxygen gas. So we illustrate that using an equation. So sodium nitrate, solid, you heat. When you heat sodium nitrate, you'll get two products. Sodium nitrite, nitrite has an NO2, but a nitrate has an NO3. So sodium nitrite and oxygen gas. So don't forget, anytime you write an equation, you should balance. So we balance by putting 2 on sodium nitrate as well as 2 on sodium nitrite. It will balance because we are going to have 6 atoms of oxygen on the left. Also on the right, there will be 6 because of this 2 times 2, 4 plus 2, that will give you 6. The same applies to potassium nitrate. Potassium nitrate decomposes on heating to get the corresponding nitrite. Remember, we have said that will be potassium nitrite and oxygen gas. So we balance as usual. So we put 2 and then 2. So Lana, we are saying that the nitrates of sodium and potassium decompose on heating to give you the corresponding nitrite and oxygen. We have said the products of effect of heat on nitrates largely depends on the position of the element in the reactivity series. So these two are at the top of the reactivity series. Therefore, their nitrates decompose to give you a nitrite and oxygen as the only products. What about those elements which are in the middle of the reactivity series? What products do they form when they are decomposed? So we are saying this, that the other metal nitrates decompose on heating to produce the corresponding metal oxide. Another product is oxygen gas, and the other product is nitrogen 4 oxide gas. Nitrogen 4 oxide gas. So this gas can be seen from the fact that it is colored. It's a colored gas, and the gas is red brown in color. So we are saying this, that the other metal carbonates, for those elements which are in the middle of the reactivity series, decompose on heating to give you the corresponding metal oxide, oxygen gas, and nitrogen 4 oxide gas. Let us illustrate that by using the following equations. So we start by zinc nitrate, zinc nitrate, zinc nitrate. On heating, from that general point, we expect to form the corresponding metal oxide, and the oxide that corresponds to zinc is zinc oxide. So we shall get zinc oxide. The other product is nitrogen oxide gas plus oxygen. So actually we shall have a mixture of the two gases, but the distinguishing property will be the color. Oxygen, as we know from Form 1, it's a colorless gas, but this one is a gas that is red-brown in color. So when we'll be performing the experiment, you'll be able to observe some red-brown fumes. So those red-brown fumes will be evidence of nitrogen oxide gas. Now remember, earlier on we said zinc oxide, the color, it has two colors. When it is hot, zinc oxide is yellow in color when it is hot. Then on cooling, it changes from yellow to white. So it's good we remind ourselves that point. The other metal nitrate is lead nitrate. Remember, these are some of the elements which are found in the middle of the reactivity series, which we have said decompose on heating to give you the corresponding metal oxide. So for the case of lead nitrate, our product, one of the products will be lead oxide, which is a solid. The other product will be nitrogen oxide gas. Then the other product will be oxygen. So we mentioned earlier on the color. Lead oxide, when it is hot, it's red-brown in color when it is hot, and then on cooling, it is yellow in color. That is lead oxide. So it's also good we remember to balance our equations. We start by balancing. We have to make this one to be even, so the best way of balancing is we put 4 here, and then we shall have 4 atoms of nitrogen, so that calls for us to put a 2 here, so that we have the 2 times 2, we shall have 4 atoms of nitrogen, and then you put here a 2, so we shall have 2 lead atoms. Then oxygen atoms will be 3 times 2, that is 6, times 2, that is 12. So let us check how many atoms are there on the right hand side of oxygen. This is 2 plus 8 plus 2, that will give you 12. Also balance in the same manner. Our first equation, this will be 2, then this will be 2, this will be 4, like that. So that's how we balance those equations. Another example is copper nitrate. Remember, I have said these are elements which are found in the middle of the reactivity series. So the products of heating copper nitrate will be copper oxide, which we said earlier on is black in color, and then the other product will be nitrogen oxide gas. Lastly, oxygen. Remember, we have said nitrogen oxide is a colored gas, so it can be seen, putting in mind that the gas is red-brown in color. So we balance once again, put 2 here, then 2, and then 4 on nitrogen oxide. Another example can be calcium nitrate. Calcium nitrate, when it is acted upon by heat, the products will be calcium oxide. Calcium oxide is white in color. Plus a nitrogen oxide gas, and then plus oxygen. Remember, we have said nitrogen oxide is red-brown in color. So we balance 2, 2, and then 4, like that. So the equation will be balanced. Now, remember, these are elements which are in the middle of the reactivity series. Those which are least reactive, their nitrates behave differently in that instead of getting the corresponding metal oxide, they give us the corresponding metal, nitrogen oxide, and oxygen. So we are going to illustrate that by using the least reactive metals, that is silver and gold, as follows. So as you know very well, silver is a less reactive metal. So its nitrate, when it is acted upon by heat, it decomposes to give you 3 products. So here we shall get the corresponding metal, and that is silver metal, plus nitrogen oxide, and then plus oxygen. So don't confuse. The other metal nitrates will give you the corresponding metal oxide, but those which are least reactive, the likes of silver and mercury, they will give you the corresponding metal, nitrogen oxide, and oxygen. So the other one is gold. Gold, my dear student, has a valency of 2, and therefore that will be the correct formula. So when gold is heated, it will give you the corresponding metal, and that is gold plus nitrogen oxide gas, and then plus oxygen. So we have to balance the 2 equations. So let's balance. Of course, check. Silver is 1 on the left and also 1 on the right. Nitrogen, 1 atom on the left, 1 atom on the right. Oxygen atoms, 3 on the left and 4 on the right. So we have to balance by making the one on the right, on the left, to be even. So that's the best way. So if I put here 2, it will mean I will have 2 atoms of silver. Then I put here 2 so that the atoms of silver will balance. Next is I balance the atoms of nitrogen. I'm having 2 atoms of nitrogen on the left. I should also have 2 on the right. So I put here a 2 like that. That will mean we also confirm oxygen atoms. On the left, this is 2 times 3. There are 6 atoms. Let's confirm how many are there on the right hand side. This is 2 times 2. That will give you 4 plus 2. That is 6. So the equation is balanced. Let us also confirm the atoms of the equation of heating silver nitrate. If mercury gold nitrate, if it is balanced, sorry. So we confirm the atoms of gold. So this is 1 atom on the left, 1 atom on the right. What about nitrate atoms? This is 2. So I'm having 2 nitrate atoms on the left, but 1 on the right. Lastly, atoms of oxygen. These are 3 times 2, 6. These are 2 plus 2, that is 4. So it's not balanced. So let us balance. So we shall put a 2 here on silver nitrate, a 2 on silver, and lastly a 2 on nitrogen 4 oxide, nitrogen 4 oxide gas. So we need to balance. Let us also confirm. So it's a matter of you have to be sure if it is balanced. So when you do that, you realize that I will have how many atoms of nitrogen? This will be 2 times 2, 4. But remember, we have 2. So it's not balanced. So that means it calls for us to make a change here. So this will be 4 atoms of nitrogen. So once again, confirm oxygen. This is 3 times 2, that is 6 times 2, that will be 12 atoms of oxygen. Let us confirm how many oxygen atoms are there on the right hand side. This is 4 times 2, that is 8, plus 2, that is 10. They are supposed to be 12. So how do you make it 12? By putting here 2 like that. So the equation will be balanced. So those are the products of effect of heat on nitrates. I want us to look at, finish by looking at the effect of heat on sulfates. Effect of heat on sulfates. Effect of heat on sulfates. Sulfates do not have so much, just brief. But from the discussion we have just had here, we have seen that the products of heating nitrates depends on the position of the nitrate, the element forming the nitrate in the reactivity series, whereby we have said the ones which are more reactive will give you the corresponding nitrite and oxygen. Those which are in the middle will give you the corresponding metal oxide, nitrogen oxide, and oxygen. Those which are least reactive will give you the corresponding metal and nitrogen oxide and oxygen. So let us look at effect of heat on sulfates. Effect of heat on sulfates. So my dear candidate, I want us to know this, that the sulfates of sodium, potassium, calcium, and magnesium are very stable. They are stable. Of course, the main reason is because those elements are reactive, and for that reason, if they are stable, it means they are not affected by heat. They are not affected by heat. That means they don't decompose on heating. The only time when they decompose is if they are hydrated. So we are going to consider the example of sodium carbonate decahydrate. So sodium sulfate decahydrate. Sodium sulfate decahydrate. This one decomposes on heating to give you anhydrous sodium sulfate, and the 10 molecules of water of crystallization. So we have said it is only possible if it is hydrated. Otherwise, if it's not hydrated, then the salt will not decompose. The other hydrated sulfates also decompose to give you the corresponding metal oxide, sulfur, a gas by the name sulfur oxide, and water. So we are going to look at an example. All right, so we have said they'll give you the corresponding metal oxide, nitrogen, sulfur oxide, and water. So we are going to consider the hydrated sulfate of zinc. So hydrated zinc sulfate decomposes as follows. we get zinc oxide plus sulfur 4 oxide and the 7 molecules of water of crystallization. The other one is copper sulfate pentahydrate. Penta means 5. It contains 5 molecules of water of crystallization. This one decomposes to give you copper oxide plus sulfur oxide, and then plus the 5 molecules of water of crystallization. So we finish by mentioning the effect of heat on hydrated iron 2 sulfate. Iron 2 sulfate behaves differently in that on heating, hydrated iron 2 sulfate decomposes to give you four products. The first product is iron 3 and 3 oxide. The other product, we have a mixture of 2 gases, sulfur 4 oxide gas. We also have sulfur 6 oxide, and lastly we shall get water. So those are the products of effect of heat on sulfates. So generally we have said sulfates only decompose when they are hydrated. So I want us to finish by looking at these questions. You'll try these questions, my dear student. Try these questions. First question: name the sulfates. Name the sulfates that do not decompose on heating. My dear student, name the sulfates that do not decompose on heating. Second question: comment on the effect of heat on sulfates. Comment on the effect of heat on sulfate. Give a general comment about the products of heating sulfates. Remember earlier on we were talking about nitrates. So our next question is write balanced equation for the effect of heat on our first one, sodium nitrate. Write balanced equation for the effect of heat on first one, sodium nitrate. The second one, lead nitrate, and lastly effect of heat on gold nitrate. So as you write the equation, don't forget to balance. So we have come to the end of our lesson for today. We have been talking about the effect of heat on nitrates and the effect of heat on sulfates. So under nitrates we have seen the products of effect of heat depends on the position of the metal nitrate in the reactivity series. For sulfates we have seen sulfates will decompose if they are hydrated. Otherwise, I thank you for being a good student. I'll see you in our next lesson. Thank you so much. How are you, learner? My name is Dickens Mugalo, and in today's lesson we want to discuss on what happens when salts are exposed to the atmosphere. So we need to know this, that salts behave differently when they are left exposed to the atmosphere. We are going to look at three categories of what happens when they are exposed to the atmosphere. So, we have some salts, my dear student, which when they are exposed to the atmosphere, they absorb moisture from the air, and that will enable them to turn into solution. Such type of salts, which when exposed to the atmosphere, absorb moisture or water vapor from the atmosphere and turn into a solution, such type of salts are called deliquescent salts. So, deliquescent salts. So, we are saying deliquescent salts are salts which, when exposed to the atmosphere, they absorb water vapor or moisture for that matter and turn into a solution. So such type of salts are called deliquescent salts, and the process that involves absorbing moisture and turning into a solution, that process we call it deliquescence. So deliquescence is coming from the word deliquescent. So deliquescence is the process in which deliquescent salts absorb moisture from the air and turn into a solution. So we are saying is a process in which deliquescent salt absorb moisture from the air and turn into a solution. So it's a process. So deliquescence is the process, but deliquescent is the salt. So we give an example of such type of salts. We have potassium hydroxide. When potassium hydroxide is exposed to the air, it will absorb moisture and turn into a solution. We also have sodium hydroxide. If sodium hydroxide is exposed to the air, it will absorb moisture from the air and turn into solution. The next class of salts, we call them hygroscopic salts. So these are salts which, when exposed to the atmosphere, they absorb moisture but do not form a solution. So they are salts which, when exposed to the atmosphere, they absorb moisture or water vapor from the atmosphere but do not form solution, but do not turn into a solution. So we are saying such kind of salts are called hygroscopic salts, and the process they undergo, we call it hygroscopy. So from the word hygroscopic, we get the word hygroscopy. So hygroscopy is the process in which hygroscopic salts, when exposed to the air, they absorb moisture but do not form a solution. So process in which hygroscopic salts absorb absorb moisture, but do not form a solution. So hygroscopy is the process, but hygroscopic are the salts. So examples of some of the examples of hygroscopic salts, we have anhydrous copper 2 sulfate. When anhydrous copper sulfate is exposed to the air, it will absorb moisture but will not form a solution, but instead it will be damp. It will appear damp. Another example is anhydrous cobalt 2 chloride. Anhydrous cobalt 2 chloride. This one also, when exposed to the air, it will absorb moisture but will not turn into a solution. The last category of salts, we call them efflorescent salts. So efflorescent salts are salts which, when exposed to the atmosphere, they lose water of crystallization and turn into powder. So these ones lose water of crystallization, and change into powder. So when exposed to the air, they lose water of crystallization and turn into powder. The process that those salts undergo, we call it efflorescence. So efflorescence is a process. So efflorescence is the process that is undergone by efflorescent salts. We have said efflorescent salts lose water of crystallization and turn into powder. So the process that they undergo is what you are calling efflorescence. So efflorescence is a process by which efflorescent salts lose water of crystallization and turn into powder. So that process, we call it efflorescence. Examples, we have examples of such type of salts. We have hydrated sodium carbonate. It contains water of crystallization, so the formula is sodium carbonate with the 10 molecules. So this one, when exposed to the air, it will lose water of crystallization and form powder. Another example is hydrated sodium carbonate. This one also contains 10 molecules of water of crystallization. When exposed to the air, it will lose the water of crystallization and turn into powder. So I want us to finish by looking at the uses of salts. We are just going to mention. Okay, so the last subtopic is on uses of salts. So we want to mention some of the uses of the salts that we know. So the first one, first use, we talk about sodium chloride. Sodium chloride, we use it as a food additive. So number one, sodium chloride. Sodium chloride is used as a food additive. Food additive. That is use number one. We said sodium chloride is a salt. Therefore, we find its use as a food additive. Another use of a salt is sodium hydrogen carbonate. Sodium hydrogen carbonate is used in making of baking powder. So my dear student, we are saying that sodium hydrogen carbonate, which is another example of a salt, is used in making of baking powder. Another salt that has its use is calcium sulfate. Calcium sulfate in hospitals, if somebody has a dislocated arm, they use calcium sulfate, which is otherwise called plaster of Paris. So calcium sulfate is used in setting of fractured bones. When somebody is injured, maybe the arm or the leg, so they use calcium sulfate, which is also called plaster of Paris. Another salt is calcium chloride. Calcium chloride is used in road surfacing, of course, involving cleaning of roads, especially in countries that are on the poles. And then another use of a salt is some of the fertilizers that we use at home in planting. Most of them contain a mixture of salts. So one of them being calcium sulfate. So calcium sulfate is used. Calcium, not calcium sulfate, sorry, but calcium nitrate. Calcium nitrate is used in preparation of nitrogenous fertilizers. So my dear student, these are just some of the uses of salts. We have quite a number. You can get them. So we are saying that today we have learned about the effect of exposing salts to the atmosphere, and we have seen salts behave differently when exposed to the atmosphere. We have seen we have some salts which, when exposed to the atmosphere, they absorb water vapor and turn into a solution. Such kind of salts, we have said, they are called deliquescent salts. Then we have those which, when exposed to the atmosphere, they absorb moisture but do not form a solution. So such type of salts are called hygroscopic salts. And then lastly, we have said we have some salts which, when exposed to the atmosphere, they lose water of crystallization and form powder. Such type of salts are called efflorescent salts. Then we have just looked at uses of some salts. So I want you to try the following questions. Try the following questions. First question: define the following terms. My dear student, I want you to define the following terms. The first term is deliquescent salt. Second term is hygroscopic salt. Our third term is efflorescent. Efflorescent salt. I want you to try and define a deliquescent salt, hygroscopic salt, and efflorescent salt. And then secondly, a state uses of some salts. So our second question requires you to state uses of some salts. Otherwise, we have come to the end of our lesson. Once again, I want to thank you for being a good student, and I wish you all the best. Thank you so much.
Welcome to Manifested Publishers.
Hello learners, my name is Stephen Kariungi, and today we continue with our topic, and our topic of discussion is acids, bases, and indicators. During the last lesson, we discussed the commercial indicators and the colors they give in different solutions. So we saw some solutions are acidic, they give a particular color with a particular acid. Other solutions are basic, they give a particular color with a particular indicator. So today we are going to discuss another indicator that is known as universal indicator, and we are going to discuss it together with what we call the pH scale. So universal indicator and the pH scale. Now, unlike other commercial indicators that we discussed in the previous lesson, we have another indicator that is called universal indicator, and this one is usually a mixture of several indicators. It's usually a mixture of several indicators, and it's the only indicator that tells us whether a solution is a strong acid or a weak acid, or whether a solution is a strong base or a weak base. All the other indicators that we have learned before, they were showing whether a solution is acidic, full stop. But they were not going ahead to inform us whether that acid is a strong or a weak acid. But for the universal indicator, this one answers that question. So it gives different colors with strong acids and different colors with weak acids, different colors with strong bases and different colors with weak bases. So you can say that universal indicator is a mixture of several indicators and is used to tell the degree or the strength of acidity or basicity. So it's the only indicator that tells us the strength or the degree of acidity or basicity. So universal indicator is used together with the pH scale. Can say that it is used together with a pH scale. With a pH scale ranging from 0 to 14, depending on the strength of acids or bases. So we'll have an illustration of the pH scale. It's a scale that ranges from 0 to 14. 0 to 14. Between 0 and 7, that's the middle. Of course, here we have acids. We have acids there. Between 7 and 14, we have bases. And then at exactly 7, we have neutral. When something is neutral, it means that it is neither on the base side nor on the acidic side. Then it has values, pH values, 1, 2, 3, 4, 5, 6, 8, 9, 10, 12, 13, 14. So at pH value between 1 and 4, 1, 2, 3, up to 4 here, these are strong acids. Up to 4. Between 4 and 7, these are weak acids. So as the acids near the pH of 7, which is neutral, they become weak. Also, the bases 8, 9, 10, as they near the neutral, they are weak bases. But as they move away from the neutral, that is 11, 12, 13, 14, these ones are strong bases. Yeah. So this is a pH scale showing the strong acids that have a pH of between 0 and 4, in between there. So it can be 1, 2, 3. That's a strong acid. If it is 5, 6, those ones are weak acids. If their bases are 8, 9, they are weak bases up to 10. The strong bases are 11, 12, and 13, all the way up to 14. So those ones are the way you tell whether. So we have the strong acids up to there, bases up to that, then finally up to that. So we have the pH scale helping us to know that these acids are strong or weak. Now, where does this value 1, 2, 3, 4, 5 come from? The universal indicator is used together with the what we call the pH color chart, or the universal indicator paper. And that paper has different colors, and each color has a pH value. So if you get a color, for example, that is red, you may find the pH value there is either 1 or 2. If you get a color that is orange, the pH value will be 3. So we can say that universal indicator is used together with a pH color chart. With a pH color chart having different colors and corresponding pH values, as shown below. So we'll still have the same pH scale from 0 to 14. The midpoint is 7. pH 1, 2, 3, 4, 5, 6. So if the pH is 1, 2, 4, 5, so we are drawing another pH scale showing the different colors. So pH of 1 and 2, the color is red. The pH of 3 and 4, the color is orange. And the pH of 5, 6, the color is yellow. At exactly 7, the color is green. So we have different colors on the color chart showing the different values. So value of 1 and 2, the color is red. That's a strong acid. 3 and 4, also a strong acid, but pH 3, yellow, the color is, the pH is a 5 or 6, that is a weak acid. So we can use it together with that. So 8, 9, and 10, here the color is blue. And then 11, 12, the color here is purple. And then above 12, the color is violet. So that is the pH scale showing various colors on the color chart. So various colors on the color chart. So if the color is red, it's a strong acid. If the color is yellow, it's a weak acid because it's 5, 6. If the color is green, it's neutral. If the color is a blue, weak base, purple and violet, strong bases. So we are saying that the universal indicator is used together with the pH color chart. Each indicator has a color chart that shows the pH values. 1 red, 2, 1 and 2 red, 3 and 4 orange as shown there. So these ones indicate the value. So the higher the pH value, the weaker the acidity or the weaker the acid. The higher the pH value, the stronger the base. So you can say that from the above, pH scale, we can conclude that 1, the higher the pH, the weaker the acid. The weaker the acid. Because we can say that strong acids have low values, weak acids have higher values. So the higher the pH value, the weaker the acid, and vice versa. In bases, the higher the pH, the weaker, no, the stronger, sorry, the stronger the base. As we can see, bases, strong bases have higher values, weak bases have lower values. So the higher the pH, the stronger the base, and vice versa. So an easier way of telling whether an acid is strong or weak, as you move closer to 7, the acid becomes weak. As you move closer to 7 on the base side, also the base becomes weak. So as you move towards 14, the bases become strong. As you move towards 0, the acids become strong. So you can also say that in this direction, we have increasing acidity. And on the other side, we have increasing basicity. So we have that. So at that point, we can have an assignment on the universal indicator and the pH scale, as we have explained. So the assignment, the first question, what is universal indicator? 2, how is universal indicator different from other commercial indicators? Number 3, determine whether the following solutions are neutral, strongly acidic, weakly acidic, strongly basic, or weakly basic. So we have solution X, Y, and Z. The pH value is given. So you're supposed to say whether it's a strong acid or weak acid, or a strong base or a weak base, or is neutral for each one of them. So we'll stop there. Until next time, goodbye.
Hello learners, welcome to Manifested online classes. My names are James Kenyani. We are going to continue our topic on loci, and we had worked out some questions in the previous lesson, and I gave you 2 more to solve at home. So we shall pick on from that stage where we shall solve the 2 questions I had given you in that assignment. So in the assignment, question 9 was state and sketch the locus, that is of a ball which rolls such that it is always 4 meters from a straight wall, and 10, a line AB rotated through 180 degrees about A. So we said you should first of all, if we start with question 9, as question 9 is blue. Let's use just black. Question 9, you go to the laws. From the definition of a locus, the law commanding the question is very important. If you look at 9, a ball which rolls such that it is always 4 meters from a straight wall. So I'll need the sketch first. So I need that sketch. Assume a wall will have some thickness. So with that, I'll know that this is my wall. So in the next one, I should look at the trajectory of the ball. So I'll come, that is my ball. So it has to roll. It has to roll. So I'll grab it. The ball has to roll. So you can take this as the initial position. That is the final. That is the final position, and that distance, we are told it is always maintained as 4 meters. So that is the sketch for question 9. So that shows a wall, a straight wall. That is the initial position of the ball. And here we shall have the path. Should indicate the path. I'll indicate the path. So if we look at T12, the path will also be a straight line because the distance is equal. Therefore, if the distance is equal, you'll just get a line. The locus will be a line parallel to the straight wall. The locus will just be a line parallel to the straight wall, because in the law they are saying it should maintain the 4 meter distance from the wall. So the path is equidistant. That's why the line will be a straight line. It is a line parallel to that straight wall. So we shall go to question number 10, the solution for it. And as usual, we always look at the law given in the question. So in question 10, it is a line AB. A line AB. A line AB. And in the definition, we talked of a line. A line will sweep out, most likely sweep out an area. A point only sweeps a path. Like in this one, it has swept a line. So we'll go straight to the sketches. And for the sketches, the instruments will play a great importance as you draw. So first of all, in that one, you identify the line AB. The line AB. The line AB. So you can draw that. So you can even use the stroke of that. So you have line A, point B. So if you look at it very well, it is the line being rotated. So in that case, A will be like AB will be like the radius of the trajectory. So you'll come, every point on the line is moving. Look very well. I'll just draw the outline. So draw the outline. Be careful there. So after drawing the outline, I'll come and make a continuation of A. So we shall have a continuation of A up to that. So it was the line that was being rotated. What you should notice, every point on that line is moving. It is not a point as in the other question. Every point on this line will be moving. So if you look at it well, it will sweep a region. It will sweep that region. It will sweep a region. So you can come and say, that is line AB. This is the final position. You can, A remains, and this can be B prime. So it is, you are given a law there. It sweeps through 180 degrees. So this is the region swept. Region swept, and it is easy to know that region swept. So the locus is a semicircular region. Be very careful. When you talk of a region, you are talking of an area. So the locus is a semicircular region. What played importance there were the laws. So from our definition of the locus, we had law or laws. So our law there was 180 degrees and then the line. So every point on that line sweeps all over. So if we have a straight edge, if I have this, and I put it on the board and rotate it, you know, it will sweep a region. So it is similar to that. So the line is just like an edge. Like if you are sweeping using the dryers, it has an edge, it sweeps an area or a region. That gives you the solution for that. Having done that, the two questions, as we continue building up those facts we've got on the definition of the locus, I'll give you two more questions on the same. I'll give you two more questions on the same before we terminate the lessons from People's Book 4. So I'll So the questions are there on the board where you are still stating and sketching the locus. 12. A rectangle ABCD is resting on its vertical plane. It is given a translation, it is moved, a translation by a vector perpendicular to AB through a fixed distance. Describe the locus. 13, a solid set square, you know what a set square is, it's rectangular in shape. A solid set square is rotated about one of its shorter sides through 360 degrees. Describe the locus. So we are still continuing to build on the definition we had on the loci before we move ahead. So as you work out the two questions, make sure you are perfecting your skills on the same as we continue to finish a few of that aspects on the loci. So having done that, I hope you'll have a good time in solving those two questions before we meet next time. So have a good time and bye.
Welcome to Manifested Publishers.
Welcome learners, my name is Stephen Kariungi, and today we continue with our topic of discussion, and the topic is acids, bases, and indicators, a topic in Form 1 chemistry. So during the previous lesson, we introduced the topic. We also discussed the objectives of the topic, and we basically introduced what are acids, what are bases, and what are indicators. So today, we're going to look at simple acid-base indicators. And these are some of the indicators that we can make ourselves. So simple acid-base indicators. Like we said earlier, there are some indicators that are commercially available. They are bought from the chemistry shops and so on and so forth. But there are also some that we can prepare ourselves. And these ones are prepared from plant extracts, from leaves, from flowers, and so on and so forth. So we'll have an experiment. We'll have an experiment, and this is to extract an indicator from flowers. From flowers. E.g., we can use hibiscus. E.g., hibiscus flower. So the procedure, the first step is to obtain the flower petals from a hibiscus plant. So obtain flower petals from a hibiscus flower. Is a plant that has some pink flowers. Then step number 2, we put the petals in a mortar and crush using a pestle. So we get the flower petals, put them in a mortar, and then using a pestle, we crush them. And then the next step, add a suitable solvent. Add a suitable solvent, e.g. ethanol or propanol. Ethanol and propanol, they are good solvents because they can dissolve the color. They can be used to extract the color from those flowers. So once you crush, as you crush, you add a solvent as you continue crushing. Then after that, decant the extract. Decant the extract obtained and use it to test different solutions. Use it to test different solutions. So the extract that we'll use it to test different solutions as follows. A, you put about 2 cubic centimeters of the solution being tested. So 2 cubic centimeters of the solution that we want to test, whether it's an acid or a base. We measure that in a boiling tube. And then step B, we add 2 or 3 drops of the flower extract. And observe. So after we have obtained our extract from the flower, of course, following the steps, we obtain the flower petals, e.g. hibiscus. We can use any petals. We can still use even some leaves of something like red cabbage. We can even use beetroot. Those are some of other examples that can be used. We crush in a mortar using a pestle, add a suitable solvent as we continue crushing, and then we obtain the extract by decantation, and then we test that extract on different solutions by putting about 2 cubic centimeters of the solution that we are testing in a boiling tube, and then adding 2 or 3 drops of the flower extract, and then we observe. So basically, what we are interested in, we want to see what color will it give us. For example, if the solution is an acid, what color will it give us if, for example, the solution is a base? So for example, if we test on solutions that are acidic, they will give the same color with this particular extract. If we test with solutions that are basic, all of them will give the same color with this particular extract that is different from acids. So we can have an explanation of that. And you can explain that lemon juice can have orange juice. We can have all these examples: hydrochloric acid, sulfuric acid, etc. all give a particular color. They all give a particular color when tested using the hibiscus extract. So all of them will give a specific color. Let's say, for example, color red. So when they give all the same color, then it means that all of them have the same properties. So all of them are acidic in this case. We can say that, on the other hand, we can have soap solution, wood ash solution. You can have caustic soda solution. All give another color. These ones give another color when tested with the flower extract. So that is an indication that they have the same properties. That means they are bases, for instance. We also have other substances that have no effect on the flower extract. They don't change their color. So you're saying that, first of all, the lemon juice, all the first ones, we can say that that is, they are acidic, all those are acidic. The ones that are giving another color, these ones, they are basic, or they are bases. And then we have other examples such as common salt and distilled water. And distilled water do not affect the color, they do not affect the color of the flower extract. They do not affect the color of the flower extract, and we basically say that they are neutral. They have no effect on the color of the extract. So the ones that are acidic, they were giving us a certain color. The ones that are basic are giving us a different color. But there are two solutions, common salt solution and distilled water do not affect the color of the flower extract, and we are saying that they are neutral. Neutral means that they are neither acidic nor basic. So common salt solution and distilled water, they are neither acidic nor basic. Now, the question comes in then, why is it that we don't use the indicators obtained from flower extracts in our day-to-day life? Now, number one is that these indicators that are made from flowers, leaves, and so on and so forth, they do not give consistent results. They do not give consistent results, and that is why they must be used only when they are fresh, when they are freshly prepared. You cannot store them for future use, right? And that is why there is need for other indicators that are more consistent in terms of the results. And also they can be used in future, or they can be kept for future use. So we can say that indicators obtained from plant extracts do not give consistent results. They do not give consistent results and should be used, should be freshly prepared. Should be freshly prepared before use. We should prepare them and then we use them right there and then. So we are saying that they cannot be stored. They cannot be stored for future use. So that is the disadvantage. In as much as they are very easy to make, as per what we have seen in the procedure, they do not give very consistent results. If, for example, they have overstayed for a long time. So they do not give consistent results, and therefore we cannot store them for future use. And that is why there is need for now what we call the commercial indicators, and that's what we shall discuss in our next lesson. So our assignment for today . So the first question in the assignment, describe the procedure of extracting an indicator from red cabbage. Number 2, why are simple acid base indicators not recommended for use in the school laboratory? So we'll stop there. Until next time, goodbye.
Welcome to Manifested Publishers.
Welcome, learners. My name is Stephen Kariungi, and today we continue with our topic of discussion. The topic is acids, bases, and indicators, topic in Form 1 chemistry. So at this point, we are going to discuss commercial indicators. And this is in addition to what we discussed the last time, whereby we discussed the extraction of indicators from plant extracts. And we saw the disadvantages of those indicators that are obtained from plant extracts, and that is now why there is need for commercial indicators. So commercial indicators give consistent results. They can be stored for a long time for future use, and so on and so forth. And we'll have various examples. We have, for example, an indicator that is called litmus. Litmus can either be in form of a solution called litmus solution. It can also be in form of a paper called litmus paper. We have other commercial indicators such as methyl orange. There is phenolphthalein. There is screened methyl orange. There are many. There are bromothymol blue. So there are several. But of course, we'll only mention the common ones, the ones that are commonly used in our laboratory.